has been created today and have achieved the near impossible.
Mars. No other planet captures the human imagination as Mars does. The reason is the striking similarity between Earth and Mars in many respects. Compared to the extremely hostile conditions on other planets, Mars, with its familiar surface features like hills, valleys, highlands and plains, polar ice caps, its relatively benign surface temperatures, and its day, which is a little longer than an Earth day, has made humans gaze at it with curiosity and excitement. For centuries, humans have observed Mars as a red dot in the night sky, moving slowly against a background of fixed stars. Because of its red color, ancient Romans named the planet Mars after their god of war. People of ancient India named it Mangala, and the same name has remained in many Indian languages today. It is also known as son of Prithvi, Mother Earth. Systematic telescopic observation of Mars began in the early 17th century with Galileo Galilei's observation, which resulted in the discovery of many interesting things and optical illusions associated with the observations, giving rise to certain misconceptions. Prominent amongst them was the belief that Mars was the abode of intelligent life capable of building gigantic canals. This firm notion in the human psyche led to dozens of robotic spacecraft, including the Mariner 9, the Viking, and the Mars Express being sent to explore the planet after the dawn of the space age. However, not one of these robotic investigators has revealed the existence of even microorganisms on Mars, let alone intelligent creatures with superhuman capabilities. Nevertheless, Mars has not revealed all its secrets. Today, there are many fundamental and profound questions about Mars that are yet to be answered. Prominent among them are those related to the evolution of Mars and its suitability for the origin and sustenance of life in the past, or the viability of microscopic life today. Thus, there is a continuous and concerted effort across the globe to explore the planet by sending orbiter spacecraft to Mars or putting landers and rovers on its surface. India's Mars Orbiter mission is an essential part of this global effort to understand Mars in more detail. India is a prominent spacefaring nation today. Besides building and launching a variety of Earth-orbiting satellites for rapid and all-round development of the country, the Indian Space Research Organization, ISRO, has now set its sights firmly on Mars and has endeavored to realize the Mars Orbiter mission. The Mars Orbiter mission envisages sending an unmanned spacecraft to Mars and putting it into an orbit around the planet, conducting modest yet meaningful exploration of its surface, atmosphere, and the space environment in its vicinity through the spacecraft is the main scientific objective of the Mars Orbiter mission. However, the primary goal of the mission is mainly technological and aims to demonstrate the technological capability of India to send a spacecraft to orbit around the red planet. The Mars Orbiter mission spacecraft is shaped like a cuboid and weighs 1,340 kgs at launch. Special alloys and composite materials have been used to build the skeletal structure of the spacecraft. Its inside temperature will be kept within safe operating limits using a host of materials, including a bright golden-colored multi-layer insulation blanket. The 3 solar panels projecting from one of its sides of the Mars Orbiter mission spacecraft generate about 800 watts of electric power near Mars. The 2.2-meter diameter dish-shaped antenna projecting from the other side of the spacecraft facilitates the spacecraft's radio communication with the Earth. In addition, it enables the accurate measurement of the distance between the spacecraft and the Earth. A variety of sun and star sensors, along with gyroscopes, enable the precise determination of the spacecraft orientation, which is very critical during different phases of the mission. The microprocessor-based control system of the spacecraft acts as its electronic brain and very accurately maintains or changes its orientation and orbit. For this, it relies on the spacecraft's reaction wheels and small rocket engines called thrusters, as well as the spacecraft's main rocket engine called the liquid apogee motor. To study the surface of planet Mars and its atmosphere, as well as the space environment near the planet, the Mars Orbiter mission spacecraft carries 5 scientific instruments which are usually referred to as payloads. They include cameras and spectrometers and together weigh about 15 kilograms. The Mars Color Camera of the spacecraft is designed to take color pictures of the surface of Mars and its 2 natural satellites, Phobos and Deimos. It helps in studying various Martian surface phenomena. The Thermal Infrared Imaging Spectrometer payload helps in the identification of Martian minerals. The methane sensor for Mars is intended for very accurately measuring methane in the Martian atmosphere and mapping its sources. Since methane is produced as a product of both biological and non-biological activities, detection of methane and knowledge of the activity responsible for its origin becomes crucial. Of the 2 other payloads, the Lyman Alpha Photometer helps in understanding the processes responsible for the loss of water from the Martian atmosphere. Finally, the Mars Exosphere Neutral Composition Analyzer MENCA payload will study the space environment around Mars. The precious scientific data gathered by the spacecraft's payloads will be transmitted to Earth through its 2.2-meter dish antenna. The incredibly weak radio signals whispered by the Mars Orbiter mission spacecraft will be received by the antennas of the Indian Deep Space Network at Bailalu near Bangalore. The Indian Space Science Data Center ISSDC, also located at Bailalu, will receive, organize, process and systematically store and distribute the scientific data gathered by the payloads of the spacecraft. Other ground stations located around the world will support the Mars Orbiter mission at specific times. The journey of the Mars Orbiter mission spacecraft to the Red Planet is a challenging as well as an exciting one indeed. The mission to launch India's first Mars spacecraft happens to be the 25th launch of the versatile and well-proven PSLV and is designated as PSLV C-25. After its liftoff, it will take about 42 minutes for PSLV C-25 to place the Mars Orbiter mission spacecraft into an elliptical orbit around the Earth. For the first time, ship-borne ground station terminals stationed in the Pacific Ocean will be used to monitor the performance of the PSLV's 4th stage, as well as the separation of the Mars Orbiter mission spacecraft from that stage. This parking orbit extends 250 kilometers on one side and 23,500 kilometers on the other side from the surface of the Earth. Later, the liquid apogee motor LAM, which is the main rocket engine of Mars Orbiter mission spacecraft, will be repeatedly fired to ultimately make the spacecraft follow a path to encounter Mars. During its 300-day journey to Mars, the spacecraft will leave Earth's sphere of influence when it will move beyond 1 million kilometers from Earth. Then it will travel in a curved path, mostly under the influence of the Sun. Finally, when the spacecraft is about 500,000 kilometers from Mars, it will come under the sphere of influence of Mars. As the spacecraft nears Mars after its 10-month-long journey, lasting millions of kilometers from Earth, its LAM will be fired again. This time, it will be to sufficiently slow down the spacecraft to enable it to be captured by Mars in an orbit around it.
On September 24, 2014, the Mars Orbiter spacecraft, after traveling 666 million kilometers, arrived at its destination in a hyperbolic trajectory. And from here, the orbiter will be inserted into the 423 by 80,000 kilometers elliptical orbit of Mars.
By going into such an elliptical orbit, you can get the full disk images of the Mars a large number of times. And as you come towards the perigee, when the sun illumination happens, you can get into the finer details.
Mars orbit insertion is a very critical maneuver, which will be carried out with the combined visibility of 70 meters ground antennae located at Canberra and Goldstone, and the onboard medium gain antenna. It may be noted that Mars Orbiter mission entered the sphere of influence of Mars on 22nd September 2014, and the final trajectory correction maneuver was carried out on the same day.
After reaching the Martian environment, spacecraft will have some velocity which is less than the Mars itself. So due to that, what happens is spacecraft moves towards the Martian center. So when its velocity is of that order of say 3 kilometers relatively with respect to the Mars, because of the gravity fall, and it is moving towards the Mars center, it picks up the velocity due to the attraction of the Mars itself. So this force is such that again, with that velocity and it is moving, we cannot contain the spacecraft with respect to the Mars. It escapes. For that sake, we need to reduce this velocity. So reduction of this velocity and making the spacecraft to move around the Mars is the phenomena what is called the Martian orbit insertion.
Mars orbit insertion phase has demanded a large amount of preparation at spacecraft level. All the operations of Mars orbit insertion will be independently realized by the onboard processor by sequential execution of events without any ground intervention. The commands required for the same were loaded onto the satellite 9 to 10 days prior to this event, that is on September 14 and 15, 2014. Mars orbit insertion operation starts with changeover to medium gain antenna 3 hours prior to liquid engine burn start. This will be followed by forward maneuver 21 minutes prior to liquid engine burn, wherein the direction of satellite is changed and reoriented, pointing it to the desired thrust direction, so that the spacecraft velocity can be reduced by a desired amount. The spacecraft is held in the same configuration for some duration. Star sensors updates are enabled after forward maneuver. 5 minutes 13 seconds prior to burn start time, the satellite is eclipsed by Mars, and hence the solar panels are unable to generate power as the sunlight is obstructed by Mars and doesn't reach it. In this case, the onboard lithium-ion 36 ampere-hours batteries will provide the requisite power by the spacecraft. However, the spacecraft is still in the line of sight of Earth and will receive data from it. Thus, 5 minutes 13 seconds into eclipse, the actual burn start event will occur.
Now in this particular mission, after we did our initial start of trajectory towards Mars, that was on 1st of December, till 24th of September, practically about 10 months you are traveling in space, and this entire LAM engine and all the connected hardware has all been shut down and it is in the switched off condition. So one of the doubt that always comes to one's mind is, when you restart the LAM engine, will it start, will it fire? To verify this, we need to check the LAM engine operates or not. And when you fire the LAM engine, for whatever duration you fire, it adds some velocity and it changes our insertion geometry and discussion. So based on this, we went through a lot of simulations and studies and tried to take advantage of a small 4-second test on the LAM engine by burning on the 2 days earlier to 24th, firing the LAM engine for a duration of 4 seconds, verifying that everything is fine so that we can operate the LAM engine on the 24th.
The criticality in this event is we need to do this operation at a particular time, because spacecraft is moving continuously with respect to the Mars. Unless very precisely we plan this operation at the time of periapsis, then it calls for some penalty with respect to the fuel, and also giving this delta V, whatever we intend to give this delta V, that also needs to be imported within some burn arc conditions to realize the final destination orbit. So with respect to time, if we are not able to do, and also your thruster is not in a position to give that required delta V within the stipulated time, there is a very possibility that spacecraft again will not be in the intended Martian orbit. So that is how it becomes more time critical, as well as it also depends very crucially on the performance of our thruster, the LEB engine, liquid engine borne engine.
The criticality of Mars orbit insertion burn lies in the fact that the orbiter should get captured without crashing into Mars or without leaving Mars. The liquid apogee motor is fired to slow down the orbiter's relative speed to the planet by 1,109 meters per second, and the velocity from 5.1 kilometers per second to 4.3 kilometers per second in relation to Mars. Getting anywhere between 200 kilometers and 11,000 kilometers will keep the orbiter in the Martian orbit. Nearly 4 minutes 20 seconds after the burn start, Mars occult starts. That is, the Mars orbiter will go behind the planet. As a result, no signal from the satellite will reach Earth for a considerable amount of time. Nearly 20 minutes past the burn start time, the orbiter is likely to come out of eclipse. And though the solar panels will start receiving the sunlight, it will continue to be operated on battery power. This is because the satellite is still not in the line of sight of Earth, and hence the switchover is not performed. The total duration of burn time is expected to be around 24 minutes. The satellite will come out from behind the Mars approximately 28 minutes after burn start. And that's when the occult will end and the satellite will once again be in the line of sight of Earth. The power generation from solar panel and telemetry will be resumed nearly 2.5 minutes after the end of occult, and data on Doppler measurement from the satellite is received, which will give the first information on the total burn performance. The reverse maneuver, wherein the satellite is once again reoriented, pointing the high gain antenna towards Earth, starts 1.5 minutes to nearly 23 minutes after the end of liquid engine burn. The reverse maneuver ends nearly 11 minutes after the end of burn. With the resumption of high gain antenna support, the Mars orbit insertion is completed. Thereafter, in the next 2 hours, the health parameters of the spacecraft will be verified, and the sequential operationalization of its 5 payloads will be carried out over a period of few days. The Mars orbiter mission had brought many new challenges before the scientists when the entire mission was being planned. designed and conceived.
We can do some good science and at a very cheap rate, and therefore since the opportunities for going to Mars is much less, only once in 2 years, we said all right, finally of course we had to use the PSLV. There were some weight limitations, but notwithstanding, the development of technologies was very important, and this was done, and it is one of the most beautiful spacecrafts with just only of course 5 experiments because we had limitation of weight. But the fact is that it was very successful experiment.
In comparison to any other mission undertaken by ISRO so far, the Mars Orbiter mission had several mission-specific challenges.
This is the first time an Indian spacecraft is going out of the sphere of influence of the Earth. Something like 9.25 lakhs is the sphere of influence of the Earth, wherein first time we are going out of the Earth's gravity and orbit around Sun and go to and reach Mars at a designated time. So these 3 domains of Earth, the Sun and Mars give rise to its own specific requirements to be met by the spacecraft.
The bus needs to cope with a wide range of thermal environment, ranging from near-Earth conditions with Sun and Earth contribution to Mars conditions where eventually eclipses and reduced solar flux give rise to cold issues.
What the spacecraft is going to experience was experimented in the spacecraft itself, and we got a good data. And later this data for the distance of the spacecraft with respect to this Sun, we normalized. And also we developed a good modeling to characterize this total phenomenon.
We had built features in the satellite which were envisaged based on the problems that were encountered by others in the past. See, whether it was in terms of redundancy, whether in terms of autonomy, what kind of autonomy features were to be built, and then making sure that you have the LAM engine for which the paths are closed. So all these were based on the failures that had occurred in the past, and then based on that, the kind of configuration we had chosen.
The mainframe bus elements and payloads are specifically designed for interplanetary mission capabilities of operating in Earth-burn maneuvers, Mars transfer trajectory, and Martian orbit environments.
This is the first time we were going to go outside and travel hundreds of million kilometers away from Earth. So this brings in multi-body problems to be addressed, like whether Sun, planetary objects, what kind of influence they have on the satellite when it travels. So a host of new areas were required. And then we also had to worry about how to keep the communication with the satellite as the distances keep increasing.
In terms of communication, communicating with the spacecraft something like 400 million kilometers was the first time. It was a big challenge. And the propulsion system, as I told, that restarting the 400 Newton LAM engine after 300 days of dormancy, which has not been done by any country, which has to be done in our case, also was a big challenge. With respect to autonomy feature, a full-scale autonomy feature need to be incorporated into the spacecraft for the reason the round-trip delay of the signal reaching the spacecraft and coming back be something like 40 minutes to the tune. So spacecraft should have autonomy to take decision on its own.
The power system has to support the spacecraft and payloads during various phases of mission, like launch phase, geocentric, heliocentric, and Martian orbit phase. The power system consists of power generation, energy storage, and power conditioning elements. One of the major challenges in the design of power system is due to the large distance of the satellite from the Sun. The power source for the Mars Orbiter mission is its single solar array wing, which converts solar energy into electrical energy by photovoltaic conversion. A single 36Ah lithium-ion battery in series parallel configuration is used in Mars Orbiter mission.
We had a very detailed discussion between the subsystem teams as well as the mission teams. the experts from various ISRO centers. Every point that came up for the discussion was debated, discussed, and a proper configuration is arrived. That is one thing. And other cost components wise, we are making our systems in our ISRO centers. So that is where, from the cost point of view, it saves a lot to us, because we are using our own human force for the sake of designing these systems, building these systems, testing these systems, and operating these systems and launching also. Every aspect, it is our own. That is how the cost factor is less.
I have no doubt Dr. Sarabhai would have himself done science. After all, he was a space scientist. In fact, why people have asked, Dr. Sarabhai was entrusted with the responsibility of building space. It was obvious to anyone in the country, any scientist in the country, because even well before space became a common thing, we were using cosmic rays to look into space.
The liquid apogee motor, or the LAM, is a crucial component of any space mission. As once the spacecraft is separated from the launch vehicle, it completely depends upon LAM for its subsequent orbit raising and attitude control maneuvers. LAM is assisted by small thrusters that are located at 4 corners on one of the spacecraft deck for controlling the orientation and direction of the spacecraft.
A propulsion system basically is derived from InSat type of spacecrafts. We have not made any element level changes. Elements are same. Where the schematic we have employed for the propulsion system is MOM, is ensured to take care of some of the redundancy concepts which are required for the particular LAM engine, which needs to work after some 300 days of dormancy in space.
For Mars Orbiter mission, the LAM burn is an important event. Firing of LAM after a journey of nearly 300 days in extreme cold and hot environment of deep space is being done for the first time by ISRO.
The criticality in this event is we need to do this operation at a particular time, because spacecraft is moving continuously with respect to the Mars. Unless very precisely we plan this operation at the time of periapsis, then it calls for some penalty with respect to the fuel, and also giving this delta V, whatever we intend to give this delta V, that also needs to be imported within some burn arc conditions to realize the final destination orbit. So with respect to time, if we are not able to do, and also your thruster is not in a position to give that required delta V within the stipulated time, there is a very possibility that spacecraft again will not be in the intended Martian orbit.
We were prepared that even if this LAM engine does not work, an alternate method by which we had 22 Newton 8 thrusters, using them achieving some kind of an insertion. To verify this, we need to check the LAM engine operates or not. And when you fire the LAM engine, for whatever duration you fire, it adds some velocity and it changes our insertion geometry and discussion. So based on this, we went through a lot of simulations and studies and tried to take advantage of a small 4-second test on the LAM engine by burning on the 2 days earlier to 24th, firing the LAM engine for a duration of 4 seconds, verifying that everything is fine, so that we can operate the LAM engine on the 24th. Those are the trials that were done, and those were also the time when a large amount of question marks were there. See, suppose when you open the LAM for operation like this, suppose there is a leakage and uncertainty, you will lose the mission. But anyway, you have to take risks to ensure that you are successful.
For achieving this task smoothly, ISRO has conducted several reviews and ground tests of LAM simulation, almost a Mars-like environment, to understand its behavior and ensure that the LAM burns successfully.
It is the LPS is responsible for that LAM engine and the thrusters. At the same time, when our systems are functioning in the satellite, we are forced to work with the satellite team. At the same time, when the requirement is coming to do the ground simulation of the LAM engine, we are dependent on the IPRC. So, as a task, we are forced to interact with the other centers, and other system also we are able to understand how our system is working with another system.
With its impeccable track record, excellent reliability and accuracy proven in the previous 23 consecutive successful flights, PSLV was a natural choice of ISRO for this prestigious mission. There was yet another key attribute for this choice, the mission flexibility offered by PSLV. In this mission, we had a unique constraint of an important parameter, orbital parameter called the argument of perigee, or AOP in short. The AOP required for our Mars orbiter mission was 282.5 degree, which was an unusually large value. To meet this, the flight regime of PSLV was extended to 44 minutes against the usual 20 minutes flight duration for our regular PSLV missions. This included a long coasting of the vehicle for about half an hour before the ignition of the first stage. Such a long coasting could be planned only with the use of 4-stage propulsive configuration of PSLV.
से आप अपने प्रथम स्क्रीन पे लगातार आते हुए Ten, 9, 8, 7, 6, 5, 4, 3, 2, 1, 0, plus 1, 2, 3. Liftoff normal. Very fantastic, steady flight of the P1 tracking. Liftoff, it is moving up.
For PSLV C-25, the long coasting necessitated specific modification and validation of the coast phase guidance algorithm and augmentation of onboard battery capacity. As the orbital parameters are very sensitive to the day and time of launch, we had to manage the generation and control of a large number of initialization files for the onboard computers corresponding to the different possible launch dates. Additional provisions were made for the thermal management of the vehicle equipment bay, and also the fourth stage, considering much longer exposure to cool space.
The Mars Orbiter mission, or the MOM, requires a major augmentation to the ground segment of the entire mission when compared with earlier missions. The ISRO Telemetry Tracking and Command Network, that is, ISTRAC, is playing a key role in the entire ground network for the Mars Orbiter mission. It is providing a backbone support in the form of ground segment readiness. ISTRAC is organizing the communication network between ground stations and control centers, computers, storage, data network, control room facility, etc. This support is for both the launch phase and the orbital phase of the mission.
There are complex systems, very sensitive receive systems in the ground station that receive the signal and the data processing system later, so that the signals are decoded properly. Similarly, for sending the commands to the spacecraft, you need to have very high power level radiation from the ground station, so that the signal received at the spacecraft will be at the order of level that is required to decode the command properly.
The launch vehicle is tracked during its flight from liftoff till spacecraft separation by a network and ground stations, which receive the telemetry data from the launch vehicle and sends it to the mission computer systems at the Launch Vehicle Control Center at Sriharikota for the mission executives. All this happens in the real time. All this information is critical from post-flight analysis that facilitates the tracking of the launch vehicle. The ground stations at Sriharikota, Port Blair and Brunei provided a continuous tracking of the PSLV C-25. Right from its liftoff till burnout of third stage of the PSLV C-25.
It required a special injection criteria. We call it as argument of perigee. So that was planned to take over somewhere in the South Pacific Ocean. Normally, all of the spacecraft separation is seen over Biak. For the MOM, the spacecraft separation is delayed further over after a long coast of the third stage vehicle, and the PS4 ignition and the spacecraft separation event was taking place somewhere over the South Pacific Ocean. So we need the regular network is not sufficient to cover this. So we here to employ a shipbound terminal. 2 ships were employed to track the vehicle over South Pacific Ocean, and also the satellite after the separation to monitor some events like solar panel deployment and the high gain antenna deployment. So this is how it becomes complex for us to configure 2 ships and deploy to that.
A new addition to the communication link network for launch support was the connectivity to the shipborne terminals. Both the ships were equipped with 2 C-band maritime VSAT communication terminals and 2 Inmarsat fleet broadband terminals to ensure the connectivity to the shipborne terminals.
The communication links from the ships itself was a very complex arrangement, and we had to activate these communication links only when they were near that near Fiji. That was the first time we could get visibility to the space satellite, communication satellite, from which the link had to be established. So our people did a marvelous job in ensuring that the links came up very fast.
Basically, any mission to Mars is a complex mission. The success rate has been low if you look at the experience of the US or the Russian group or even the Europeans. Now, when you look at the Mars mission that we undertook, time was the essence. We wanted to do it in the next possible opportunity, November 2013, and we were at July 2011 when we decided internally to go for this mission. So we had to first prepare a spacecraft within 15 months with autonomy built into it. Second, we needed to put the spacecraft into an orbit around Earth to ensure minimum energy transfer from Earth orbit to Martian orbit. It required a redesign of the PSLV and a new mission design for PSLV. The next aspect is tracking and navigation. Deep space network was essential. We needed to augment our deep space station at Bailalu. And also we needed to have the position determination capability. Then when the spacecraft goes from the Earth's orbit towards Mars, what are the influences? How much is the influence at each point of time from Sun and other planets? We need to estimate this precisely. And time delay. The communication is an important issue from distance and time. So we needed to handle all this and prepare a spacecraft without compromising on any test and evaluation process.
It was really work for ISRO Satellite Center as a lead agency for doing manufacturing the satellite here, but we had contributions from all other subsidiary centers, SAC Ahmedabad and IASU, or from LEOS, or from VSSC, and all those people together. And of course ISTRAC was the primary center for receiving the data. All of them really converged, and we could make the satellite in a fairly feverish manner, but it was really required for us to really be feverish because the schedule was really against us.
What were the contributions of Vikram Sarabhai Space Center for the Mars Orbiter mission? The main thing is the Mars Orbiter mission has been executed using the Polar Satellite Launch Vehicle PSLV. That was a great thing. And of course, we could provide the launch vehicle support with a very proven and one of the most reliable launch vehicles in the world is the PSLV. That is the one thing. In addition to that, in the spacecraft, the orbiter and the spacecraft, we have very accurate contributions, very systematic contribution with respect to two areas mainly. One is in the pyrotechnics. In the all spacecrafts contains systems, valves and regulators which are actuated through pyrotechnic devices. All those things are all supplied by a group called the Space Ordnance Group in VSSC. Then all the spacecrafts also has contained a lot of composite elements. That composite elements, components and certain attachments, brackets, antenna systems, etc. is made by the composite entity of Vattiyoorkavu, is a part of the Vikram Sarabhai Space Center. And the chemicals group in this center has provided a lot of thermal coatings, adhesive thermal coatings and thermal paints for thermal management of the spacecraft. Added to all these things, our prestigious laboratory, the Space Physics Laboratory, has developed a very sophisticated, first time, very novel instrument called MENCA, which is there in the orbiter and performing wonderfully well and giving us data.
Mars Orbiter mission, ISTRAC has played a very significant role. It was involved in different phases of the mission. It had a major role in providing launch support to this mission. It also had a major role in terms of supporting the spacecraft operations. ISTRAC normally provides launch support, that is basically the tracking of launch vehicle and providing the launch vehicle telemetry data to Sriharikota for almost all of ISRO's missions, whether it is PSLV or GSLV. ISTRAC network provides this telemetry support to all the missions. But Mars mission was really special. There was a lot of complexity in supporting Mars mission, and a very high level of logistic challenge, both in terms of the scope of support as well as the time which had to be met. Everything was special for MOM. It's not that you can single out one or the other. preparing the IDSN 32-meter antenna for MOM was the first time we were preparing this terminal for deep space support. Though it had successfully supported the Chandrayaan-1 mission, when you consider the distances involved with respect to a lunar mission to a Mars mission, this was a much higher level of challenge.
Space Application Center Ahmedabad contributed 3 payloads to the Mars Orbiter mission. They are the Methane Sensor for Mars or MSM, the Mars Color Camera or MCC, and the Thermal Infrared Imaging Spectrometer or the TIS. Now, these 3 payloads are essentially meant to investigate, scientifically investigate the Martian atmosphere as well as Martian surface studies.
The Laboratory for Electro-Optical Systems have made very significant contributions in the Mangalyaan mission. These are the high accuracy star tracker, the second generation star tracker. This is called Mark II star tracker, which will provide the directions of the Mars orbiter mission in reaching the Mars mission. Apart from that, we have the Coarse Analog Sun Sensor, which will give the direction cosines of the sun in the body frame of the spacecraft. We also have solar panel sun sensors, which will help you to orient the spacecraft solar panels to the required direction in order to generate the maximum solar power. And in addition to that, we have the instrumentation electronics, which will cater for finding out the various temperatures of the spacecraft. This will help us to maintain the spacecraft in very good condition and then handle all the thermal requirements of the spacecraft. As you know, in reaching the Mars, these directions play a very important role. The importance of direction is when the Mars is actually at the time of the spacecraft launch is far away. It is going to come after 9 months into the desired position, and the spacecraft is going to have a rangeous onto that particular position. So this is helped by the way of directions. So the directions are basically imaged by, there is something called, I will give you an example of this. This is a stellar space, wherein if you look into the space, you will see a kind of star patterns, so many patterns. We have Arundhati, Saptarishi Mandala we call it. Like that there are so many stars. Ancient Indians have been very good in this kind of a spherical astronomy, wherein they have catalogued a lot of stars, and then the spherical trigonometry laws have been characterized by our ancient scientists like Aryabhatta and all. So now we are using the similar principles and develop an instrument called Star Tracker, so which will look at the star patterns and then tell us the direction of the spacecraft, whether it is going in the right direction or not. So this is the most important instrument which has been developed in Laboratory of Electro-Optical Systems. This is a payload which has again been developed for the scientific observations in the Mars orbiter when the spacecraft orbits around the Mars. This is basically to find out the evolution or the history of evaporation of water vapor from the atmosphere of Mars. It is believed that there was water in Mars a few million years back, and it has totally eroded in the recent months. As you look at it, it is all fully desert kind of a situation. So how this water vapor erosion has occurred, is still some water vapor left in the Mars atmosphere. This instrument is going to find out the details of this kind of thing by observation. This is done by an instrument called Lyman Alpha Photometer. There is a photometer which will find out the radiation that is coming out from the atmosphere, and it will be observed in 2 particular bands.
This task is always going beyond the center's limit, especially MOM. It is not constrained to one particular center. We are talking about that, the propulsion module. You know very well the LAM engine, whatever fired fantastically on the 24th September, as well as the thrusters. It is really supplied by LPSC, whereas the satellite is built by ISAC. The payloads supplied by this one. If you see that total as a MOM, this is going beyond the center's boundary.
We can do some good science and at a very cheap rate, and therefore since the opportunities for going to Mars is much less, only once in 2 years, we said, all right, finally, of course, we had to use the PSLV. There were some weight limitations, but notwithstanding, the development of technologies was very important, and this was done, and it is one of the most beautiful spacecrafts, with just only, of course, 5 experiments because we had limitation of weight. But the fact is that it was very, very successful, the experiment.
ISRO has all along been looking at how to bring in the space technology to address the issues and concerns of our country and our countrymen and our government. So it will continue to be our single most priority item. All the other things we will be doing is only to improve the scenario, to address how we can bring in this space technology to address the various aspects of society, to bring better quality of life to our countrymen, and also to enable government to do its governance job by providing meaningful and useful information on the basis of which decision making becomes possible.